Regardless of where you stand on the matter of data science sexiness, it's simply impossible to ignore the continuing importance of data as well as our ability to analyze, organize, and contextualize them. Data are changing how our businesses and societies function. They are being used to solve a ton of interesting problems and shaping the questions we can ask of the world around us. Hi, I'm James Lee, and this is DataCast. Join me for raw conversations with practitioners from the worlds of AI, machine learning, statistics, and data science. Hello everyone, welcome to a new episode of DataCast, and today I have the pleasure to be on a call with Dreda Mishadovic. Dreda earned her PhD in the Applied Algorithms Lab of the Computer Science Department at Stony Brook University in New York back in 2014. She has worked on a number of projects in algorithms for massive data, taught algorithms at various levels, and also spent some time at Microsoft. She is passionate about teaching, promoting computer science education, and technology transfer. Now she's worked as an assistant professor of computer science at the International University of Sarajevo. So, Dreda, welcome to the show.
Thank you for having me. Hi.
By way of introduction, I saw that you got your bachelor degree in computer science from the Sarajevo School of Science and Technology back in the mid-2000s. Can you describe your undergrad experience there and some of your favorite CS courses you studied too?
Sarajevo School of Science and Technology was a specific story because that was the first year when that university was started. I was the first generation to enter this university, which was actually the first private university here in Bosnia. So probably I wouldn't expect you to be familiar with the Bosnian system of education, but unlike in the US, up until recently, there was only state universities. So everybody would just study at the state university. And this university was just starting, and the lectures were all in English, and it was promising to offer modern education with, international faculty and so on. So it sounded exciting to me. So I started in a cohort of 60 people. So there was a total of 60 of us. And I have to say, it was a really unique experience. It was a really unique time because we didn't have that many resources, but we had a lot of enthusiasm. And the professors who worked there, they worked on kind of building a new institution very passionately. So we had a lot of one-on-one contact with the professors. And we also, kind of all became friends. I know that when you are, at a big university and you're sometimes taking a class, like a lot of times you don't know the people in your class because, every new class you're kind of taking with a different group of people. Here it wasn't. Here the system was that everybody was taking the same classes. Like if you studied computer science, there was a predetermined set of courses you took. So basically, I couldn't really choose to take more algorithms or more math or anything like that. We all took a set of, fundamental courses. But something that I really would emphasize about that experience is that we had a lot of personal communication with our professors. So for somebody who has spent all of their life in Bosnia, in Sarajevo, now you have an American professor who came in and, they kind of open your eyes and they, inform you a lot about many opportunities, which I would say helped me a lot to feel brave enough to go abroad and study abroad and so on. I would say that's what kind of made it special. And actually, even today, because like a lot of people still live here, even today, our cohort, we kind of meet up on a yearly basis. I would say that a lot of people from that generation went on to start their own businesses or go for graduate degrees and stuff like that. So I would say it was a really exciting group of people to study with. As for the courses, it was just a standard computer science curriculum. I would say, algorithms, discrete math, those were some of, my favorite courses.
I'm just curious, why did you decide to study computer science in the first place?
That's a really good question. When I was in high school, I really liked all the courses. I liked everything. There wasn't a single thing that I said, I hate that course. But I liked math the most, and I liked languages. So, and this university was a new university where lectures were going to be in English. I know that's now common, but like 15 years ago, it wasn't so common, especially where I lived. So, combination of that, and I had a feeling, I had a hunch that studying computer science would be similar to studying math, that I would get to use some of those skills. But I didn't know that. So I went to the website to look at the curriculum of the computer science program. And I remember looking at courses called computational complexity, algorithms. And I was like, yeah, this kind of sounds like math. And it's funny because, today you could just go on YouTube and learn what that course is about. But back then, that really wasn't the case.
Mhm.
So I had a hunch about that. And it proved totally true, because here people would tell you, like, if you're good at math, you should study electrical engineering, because that was kind of, you're going to get a job if you're an electrical engineer. But I wasn't into that. There's a side of math that's much more related, especially discrete mathematics, that is very much related to, how good of a programmer you're going to become and a problem solver and so on. And actually, one thing that I would emphasize from my undergrad education is we had a professor, his name was Douglas Van Wieren. He used to be a coach in the US for these ACM regional programming competitions for his team at a university where he worked. And he introduced us to this contest and the fact that we can go on that kind of contest. So there was a small group of us who practiced those problems a lot. Like now, there's a lot of these sources like Geeks for Geeks and Lead Code and all of these sites where you can practice. Back then, there was just this competitions and Olympiad problem sets.
Mhm.
And that's where I fell in love with programming. That's where I felt like that was in my second semester. And that's when I started solving those problems, I felt like, yes, this is what I really like doing. Like I sometimes wouldn't sleep all night trying to think of a solution to some problem. So that's when, it kind of all started.
Fabulous. Yeah, thanks for sharing the stories and your journey in going from math and then solving those problems into more concrete computer science study. After finishing your bachelor degree in 2008, you moved to the US to start a PhD in computer science at Stony Brook University, and there you were advised by Michael Bender. Well, how was your overall academic experience in the US?
I applied for a PhD right out of college. Basically, it was to be honest, at first it was really shocking for me to go to another continent. And at the same time, you kind of face a lot of challenges. Like you both go to a new place to live on your own, to be very far from your family. I know that's not shocking for a lot of undergrads going away from their home. I'm saying how it was for me. And then you go to a huge university where there are a lot of really smart people. So I would say at first it was like a huge reality check, because you kind of go from being the best student in your class to definitely not being the best student in your class. But it's a really useful experience. And that was the first kind of a first time, because like the whole PhD is first you go through these courses and then you do research. And the research part is really where you learn how to be kind of an independent academic and think about problems in a kind of your own original way. I mean, overall, I felt like it was a very challenging, but probably like the best thing I've done. And I was very lucky to be advised by my advisor, because Michael Bender, he was on one hand an academic who worked in the field of algorithms. So basically, if you look at his papers, you would mostly see, a theorem proof, theorem proof, theorem proof kind of a structure. But at the same time, he started a company where they designed a database engine based on algorithms and data structures that they studied in theory. They decided to practically show that some of these things that they're saying are really efficient are in fact really efficient. So I was really fortunate to have that kind of exposure, because it's very rare It's not a rare for a faculty member to start a company, to start a startup, but it's kind of rare to have somebody from algorithms, a very theoretical field, start a company where they're using those things. So I would say I was really lucky that my PhD was informed by those insights, because he would come back from his company and he would say, you know what's really interesting? Like my PhD thesis was a result of one of those insights where in theory you make some assumptions, but then you go into practice and you see that that's not the case. Well, can we write a paper about that? Can we see how our algorithm works in the real setting? I would say it was a really challenging experience. It was lonely at times. Being a PhD student is really kind of a rite of passage, the kind of angstiest time of your life. And I look back at it in retrospect like a great time, but I remember at that time it wasn't that great. So, and something that I really liked was the competition and this real passion for research and passion for work, that America is one of the countries where you can really experience that. I was really fortunate to have that opportunity to study there.
Fabulous. I guess like you talk a lot about like within the CS department. How about like Stony Brook overall as an institution? Yeah.
Stony Brook was actually a really, really amazing school. I'm saying this because I applied to Stony Brook by accident, in a way, an accident. I mentioned the Olympiads, the contests I was going for. There was a book for how to prepare for those contests, and a professor who teaches there at Stony Brook, Steve Skina, wrote that book. And that's how I learned about Stony Brook. Like if you're in Bosnia, you kind of know about a couple of Ivy League schools and that's it. So I kind of, just because of that, applied to Stony Brook and I ended up going there. Stony Brook was a great place academically, but for a student who is, let's say, an undergrad, I would say it's a little bit, it suffers from the fact that it's really close to New York City. So they're not trying that hard to turn that place into a community because, you know, New York City is an hour away. And so there's a lot of commuters. So socially, Stony Brook might not be kind of the best place to be. It's a little bit like, I would say it's a little bit isolated. But academically, it's a really amazing, it's a really competitive place. Also, I know there's a lot of, you know, expensive universities in the US. I would say Stony Brook is one of the places where studying as an undergrad is not that expensive, but you get a huge value for it. I remember that I was doing an internship in Microsoft, and recruiters from Microsoft told me that they definitely come to Stony Brook every year. They have a small set of universities they come to, but they always choose Stony Brook because they always have really great candidates from it. So I really liked Stony Brook, but I kind of didn't like that isolation side of it. That might have to do something with the fact that I came from a place where it's a really tight-knit community. Right. So being on a campus and, you know, just driving back home and between home and campus and my life being pretty much that, felt a little bit lonely. But at the same time, I don't know, if I were doing my PhD in the middle of amazing New York City, God knows what would have happened. So maybe this was for the best. But yeah. You know, academically speaking, I would say Stony Brook is a really great school.
Yeah, thanks for going over some of those trade-offs between both academic and social life. So let's dive a bit deeper into some of the research that you work on during your PhD. Your PhD thesis is titled Upper and Lower Bounds on Sorting and Searching in External Memory. For listeners who are not familiar with sorting and searching in external memory, can you just go through some of the key research problems that you address?
Sure. If you're a computer science student, you probably, you know, by the time you graduate, you definitely had to take a course in data structures and a course in algorithms, or, you know, a course in algorithms and data structures. So what you normally learn there is that regardless of whether you write a program in Java or Python or C++, there's an underlying idea behind that program. And depending on how good of an idea you have, basically how good your algorithm is, that determines how fast your program is going to run. And that shows more and more the more data you have, right? So an algorithm is a really important aspect of building programs. Basically, it's a recipe for how to build a program. Now, what has been happening recently, especially, is that the amount of data that we're dealing with is growing at a tremendous rate. However, that wouldn't be such a problem if development of computer hardware were going at the same pace. So for example, if you take in 80s, right, you had RAM memory that's of size like 2 megabytes or 4 megabytes, late 80s. And you had data sets that are, like maybe an order of megabytes, like a large bank would have to do like 100, like a 2 million checks, which is kind of a ridiculously small number now in terms of size of a data set. Now, ever since, data has grown in size at a much faster rate than the RAM memory has grown in size. So now what's happening is that if you want to design an efficient algorithm, what you need to pay attention to is how fast the data is going to be transferred from cloud, from a disk, from SSD to your RAM memory where the computation can be done. So basically, if you're a student who's taking algorithms and you're worrying about, how many comparisons does a quick sort need, or how many comparisons does a bubble sort need, that's now kind of less relevant, because the main aspect of the problem is not the number of computational steps the algorithm has to take, but how much time it spends in moving data back and forth. Mm-hmm. So because why is that important? Well, it's important because moving data, let's say from a disk to RAM, that's something that works on the level of milliseconds, like you can do thousands per second. Whereas computational steps that take place in RAM, you can do like a billion of those per second. So you clearly need to optimize this more expensive thing. So basically, that's what my thesis was about. The field of external memory algorithms, basically the ones that put emphasis on the data transfer cost and they kind of neglect the computational cost, that existed way before my thesis. So for example, instead of merge sort and quick sort and bubble sort, now you have external memory merge sort and external memory quick sort. And in really big data sets, those are the algorithms that are important. Those are the most efficient ones. So that's generally about external memory. But what my thesis was about, as it usually happens with PhD theses, that you're solving a tiny aspect of a problem, is that I worked on a particular variant of a sorting. When you have a database, and in a database, you can have items that are of varying sizes. So you can have records, some are really small and some are really big. So when you have that kind of discrepancy, the efficiency of a sorting algorithm also changes. So that's a problem that I was dealing with.
I see. Yeah. Thanks for sharing some of those details related to your dissertation. As a core assess of this thesis, your paper, Don't Trash, How to Cache Your Hash on Flash, describe the cascade filter, which is an approximate membership query data structure that scales beyond main memory. And this is an alternative to the well-known Bloom filter data structure. Could you mind going over some of the details of this research?
So this was a cool paper from my perspective, because we ended up collaborating with another lab, a storage lab. And basically, it was an interesting thing because in order for their system to run, they were looking for a particular data structure. And we, on the other hand, were algorithms lab who could think of something like that, but didn't have the application. So there was a third professor who kind of connected us to each other. But basically, the idea of that paper is that now there's a number of these succinct data structures. Bloom filter is one example of such a data structure. For people who don't know what the Bloom filter is, it kind of serves a similar purpose as a hash table. Basically, it tests the membership of items really quickly, but it does it in a smaller amount of space. So it's a much more space efficient data structure than a hash table. So in many applications where you would normally use a hash table, but you have a really big data set, you might want to use a Bloom filter. And Bloom filter is really popular. Like pretty much every company nowadays uses Bloom filters for those purposes. However, when you're using a Bloom filter works based on hash functions where you're setting particular positions, like kind of random positions. In Bloom filter, you're setting those bits to zeros and to ones and so on. And the problem is when you move that data structure to a disk, then that becomes like a random writing all over the place. And that gives you a really slow performance. So the benefits you would get from space are kind of canceled out by the disadvantage of spending a lot of time doing random writes. So what that paper did is that basically designed a data structure that is functionally like Bloom filter, but it in fact has a much faster performance because it manages to do these linear scans over disk.
Mm-hmm.
So this is something that I think is interesting for people who are nowadays doing algorithms for big data, that you really need to keep in mind the architecture of a computer. You know that for a disk, for example, random operations like random reads and writes are much slower than the sequential ones. Right. So if you have a way of changing your algorithm or data structure to have a data access pattern that is kind of gliding over the disk that is sequentially accessing data, you can gain a lot of performance. So this is one of the areas of intersection between algorithms and kind of computer architecture. This research made use of that. So we ended up designing a data structure called cascade filter that has like I believe about 2 orders of magnitude better performance than if you put Bloom filter on disk. Being somebody who does theory and algorithms, that was one of the more practical experiences for me because, we were writing code and writing experiments for it. It wasn't just theorems and proofs of theorems. So I thought that was cool, that side of the project.
I see. That is a collaboration with the storage lab, right? With the people with more application focus.
Yeah, exactly. It was really cool because I think, and generally, this tends to be a difference between industry and academia a little bit. They were kind of the more industry, even though they're academic lab as well. They had really cool problems. And in industry, I think you encounter really cool problems that you don't necessarily have time to solve, or sometimes you don't have the knowledge to solve it because you're kind of focused on delivering a product and deadlines and stuff like that. Whereas people in academia have all the skills to solve a particular problem, but they don't have the problem. And sometimes in theory that happens, that people are kind of inventing their own problems.
Mm-hmm.
And, theoretical papers are sometimes littered with statements like, this might have applications in X, Y, and Z. And sure, it might. I mean, it did happen a lot of times that mathematicians invent something just because it's beautiful and interesting, and 200 years later, it's the thing we can't live without. That does happen, but I think it's really cool when you solve a problem and you see the impact of you solving that problem. So this was kind of similar to that because those guys, they had a problem they needed to solve and, we could help them. So that was a really cool feeling.
For sure. So another publication coming out of your PhD, this one is called The Batch Predecessor Problem in External Memory. So this work studies the lower bounds in 3 external memory models, the I/O comparison model, the I/O part and machine model, and the indexability model. Can you elaborate on this research?
So this is a little bit more of a theoretical paper. I guess for your listeners, the first thing I would like to clarify is, lower bounds. What's a lower bound? So you have kind of a side of computer science of algorithms that's engineering, right? You have a problem and you're trying to come up with the fastest algorithm. On the other hand, you have something that's more like science, which is lower bounds. Lower bounds really study the properties of some problems. And that's kind of the more mathematical side of things, because you could take any problem you're working on, like sorting problem, or I don't know, matrix multiplication, or any fundamental problem, and you could ask yourself, what is the limit to how efficiently this problem can be solved, right? Because if I have an algorithm for a problem, I don't know whether that's the best algorithm. Somebody might come along tomorrow and say, I have a better algorithm, right? So lower bound serves to tell you what is the limit, like what is the best that's possible for a given problem to be solved. And that's something that's going to be true in 100 years, in 500 years, and so on, given, of course, the computational model that we're talking about. Like if somebody comes along with a quantum computer, of course, a lower bound that's for a Turing machine, for, the computer we have now wouldn't be valid because quantum computer is a different system. But given a particular system, lower bound is there forever. So what that paper dealt with is how fast you can solve a particular searching problem on disk. What that translates to is when you have like MySQL database, for example. MySQL database is based on a particular data structure that's called B tree. And B tree sits on disk, and you pull information from B tree in order to find something. And basically, what the lower bound problem is asking is there a better way of doing it than using a B tree? And it turns out what that paper showed, that generally no, for a single element, for searching for a single element. Actually, that's something that has been known without our paper. It has been known before. But what we showed is that when you're searching for multiple things at the same time, you might actually do better than what B tree would do. However, you need to pre-process data to the point where it's not really practical. So translating this to kind of English language, what I mean is when you are working with multiple elements, right? Let's say I am in parallel trying to solve a couple of problems. I benefit from trying to solve many of them at the same time. It's like a carpooling idea, because when you're transferring data from disk to RAM, that's a really expensive operation. So if I'm going to actually do that, then I might as well use that data transfer to solve a lot of problems in parallel. This is kind of a really cartoon version of the problem that I'm talking about. But basically, this batched problem is something that can be more efficiently solved than if you're just solving one single search problem. But as I said, the amount of pre-processing that you would need is so high that it wouldn't be a really practical thing to do for a company, for, to implement as their solution. But what paper says, it's possible, right? Mm-hmm. Whether it's practical or not, that's not our problem in that paper.
And you said this is a more theoretical paper. I'm just curious, like the deliverable is essentially the theorem, like a proof that you showed that.
Yes, exactly. Theoretical computer science, it's really a sort of math, because you are proving there's a certain set of tools that you can use to prove theorems, not to kind of become, actually the basic thing that we used in this paper is something called information theory. And information theory talks about what is the least information. If you make a step, let's say I compare A to B in a sorting algorithm, how much information that gives me and how much information do I need to solve the entire problem. So yes, the deliverable is proof of a theorem.
Thanks for sharing that. Yeah, definitely, like data transfer, this new idea, this is something I'm still unfamiliar with. So So this is really some interesting problem that might have an impact for the future. So at Stony Brook, you were also a teaching assistant for the Introduction to Algorithm course, both at undergrad and graduate level. What have you learned about teaching that has impacted your decision to become a professor later on?
Well, I've always kind of liked teaching. Right now, I mean, if you're a professor, teaching is one of those things that in a modern academic setup, professors really spend most of their time doing research, not doing teaching so much. And what I like right now, actually, about teaching is it's something that has immediate benefit. It's something that you do on a daily basis. And on a daily basis, you see students learning and changing and becoming these individuals and professionals. And I would say kind of a mentally healthy, good thing for a professor is to teach. And also, if you're a procrastinator, it's a really good thing because it has a set time when you need to go to the lecture. So you can't change the time. You have to be there at that time. And I feel like it's a really good thing to do on a daily basis. It's a good way to understand a topic. If you don't understand it by teaching it, you can understand it better. I'm always surprised when I teach the same topic for fifth or sixth time in a row. Every time I learn something new and I understand it better for the next time. I mean, the main thing that I like about teaching is sharing knowledge in this social setting. I like people and I like knowledge. So teaching is those two in one. I guess that's the answer to your question.
Definitely. I guess at this point you are the TA while you are a PhD student, right? And then I suppose the student in your class have a variety of knowledge about algorithms, for example. Let's say for the student who at the time was struggle with algorithms, what are some of the things that you help them to at least become a little bit better in these classes?
So something that I've learned over the years, and I think I'm going to keep learning over the next years, is that one of the issues when you're teaching algorithms is they are taught as an abstract theoretical subject. And sometimes, for some reason, I guess the professors very often don't make the connection between the design of an algorithm and the implementation. And something that I think really helps students is if you actually show them or write the code for the algorithm, if you show an example, because people who teach algorithms are often, they're researchers in algorithms. So they are interested in the high level idea. They're not interested in low level implementation details. So they are interested in, is there a better algorithm and blah, blah, blah. But they're here, they're they understand that algorithm and it's sometimes hard to empathize with a student who knows nothing about it. So what really helps is if you just open your editor, your coding editor, and show how it works. And all of a sudden students are going to be like, oh, well, that's it. Okay, I get it. And I think that's something that, when I just came back from the US and started teaching for the first year, I was teaching, theorems and proofs, because that's something that I thought was challenging and sophisticated and interesting. But over time, I'm kind of now simplifying over time. Now I'm more and more showing the pieces of code and how you implement something, because I think that's something that students will find useful when they graduate. They might not remember, and they most definitely will not remember the theorem or the proof, but they will remember how some piece of code worked, how something was optimized, and so on. And that's the side of algorithms that is really useful for their future careers.
For sure.
So I find it that because academics have this tendency to think abstractly, that's what helps them solve problems, then they often don't think about kind of lower level details. Or sometimes you would see professors say oh, you can do examples at home. I'm going to tell you about the abstract concepts and you can do examples at home. It's like, no, do the examples in class, and then they can later integrate that knowledge into something more abstract. So I think as the time goes by, I'm seeing more and more value in teaching concretely versus abstractly. I think that helps all students, not just the struggling students.
Definitely that tying the theory to the practical knowledge is certainly very important. During your PhD, you also interned for 2 summers at Microsoft under the Server and Tools division, which then was actually headed by Satya Nadella. What were some of the software development projects that you were involved with during this internship at Microsoft?
Yeah, I was an intern for 2 years in Microsoft, I believe 2011 and 2012, if I'm not wrong. I had a great time both summers. The first summer I was in System Center team where they were working on the app called App Controller. So this was the time when this kind of businesses were starting to move their services to the cloud. And now it kind of sounds like, of course, everybody has a cloud, but back then it wasn't so much the case. The goal of this app was to enable people who work at a particular business, let's say Target, that if there's something wrong with the service, they are the ones that can see what's happening. They can restart the service, they can delete it, they can see whether some service is stuck at what location and so on. So the goal of that app was for enterprise clients to get more insight and control of their services. But one of the problems with App Controller was that when you load the dashboard, the loading time for services was really long. Like if you switched between tabs and then you went back again, you would wait for a minute, and then you go to another tab and then you again wait for a minute. And the goal of my project at first was a proof of concept. It was like, how do we decrease this response time? And the goal was to develop a cache, right? And the cache would store all of this stuff, so it would speed up the application. Now, the interesting thing that happened during this internship was that one day, maybe like 2 weeks into my internship, the manager of the team came back and he said, like, we just had a meeting and now, the clients were pissed off with the delay time and so on. So now all of a sudden this cache has to be implemented with the product by the end of summer. So now my project that was at first just, a proof of concept type thing, something we might do in the future, became a feature to be implemented in the next 2 months. And then I got really experienced software engineers added to my team, or should I say I was added to their team to work on this cache. And I got a lot of amazing experience from working with these people and looking at them write code and writing code with them. And the second summer was similar in that I was supposed to design this app for visualizing the performance of different services. So still it was not in the same team, but kind of the similar idea. The first one was more technical though. And I really loved Seattle. So second time I kind of came back a little bit because of Microsoft, but also a little bit because of Seattle, because it was really, I really loved being there. I love Seattle.
Yeah, for sure. You talk about though that because of some of those business requirements and you actually have to learn all this concrete software engineering knowledge during your internship. What was that process actually look like? Because your PhD work mostly focused on the theory side, and then now you got exposed to a whole new level of industry requirement on how to make software practical. How does your mental models kind of switch within this?
Yeah, that's a really good question. The interesting thing is if you're good at algorithms, you're going to get an internship or a job in a software company very easily because those are the skills that are being tested, right? I'm assuming you're a computer science student, right?
Mm-hmm.
So if you're joining a company, you probably had to go through the software engineering interviews that mostly do include algorithms and data structures and coding, but then you go to work and it's not at all about that. I guess something that I liked about industry is that you are kind of in touch with what people need. All right, you're imagining all these different kinds of scenarios, and the human side of things is really important. in theory, in algorithms, it's a kind of a more of a lonely endeavor, because you can sit on a tree and work with proving a theorem. And of course people work in teams on papers, like it's not just by yourself, but still it's mostly individual, and then those individuals come together to put a paper together. But when you're in industry, it's all the time you have a customer in mind and you're working with other people. So it's a much more social experience. However, you're also something that I didn't like about industry so much is that depending on how, bosses decide things, like today this is important and tomorrow this team doesn't exist anymore, moving on, everything moves so fast. In academia, there is kind of like it's a little bit of a slower pace. So yeah, it's definitely different mental models. But something that I think is changing a lot and very fast is that a lot of people are now moving from academia to industry, which is making industry much more creative and much more prone and interested in doing research. I thought Microsoft was a really exciting place to be, and I really learned a lot there.
Yeah, thanks for sharing those stories. So after finishing your PhD, you returned to Sarajevo School of Science and Technology and work as an assistant professor of computer science. Can you talk about this decision to continue with academia and become a professor?
Yes, well, that's kind of an ongoing dilemma in my mind. I wish I could say something smart on this subject, but I always liked teaching. For me, really, the main motivation for an academic job was contact with students and sharing knowledge and the freedom, It's kind of a different concept altogether from working at a company from 9 to 5. So I really like that about it, academia. However, coming back here, being a professor in Bosnia is very different from being a professor in the US. Something that attracted me to coming back here and teaching is that I felt like I learned a lot of new things that I felt people and students here could benefit from, because there's not such a huge number of people that go abroad and come back to share that knowledge. Mostly, like most of my colleagues who graduated with me, they stayed in the US. So that was one side of things. Like I felt like I have something to contribute in my community. But also I had personal reasons. I have family here. I wanted to be close to my family. So I would say my decision was actually more driven by that than anything else. One of the negative things about research, about, academic job in Bosnia is that our government doesn't give many funds for research. And actually, the US is a great example of how that system works. Like, professors apply for grants and they get grant money from the government, and then they employ students who are their graduate students to work on research, and they produce more research based on which they apply for new grants. And it's a really good system. And in Bosnia, that system really doesn't exist. So if you write a paper, good luck finding funds to go to a conference to present it, which is why Bosnia, unfortunately, doesn't have a good research output at all. Mm-hmm. So you have to work on research in like your free time, because you have so much teaching and so many administrative duties that research doesn't really come first.
Right.
And that's a pity in a sense, because for you to be a good teacher, you need to learn new things all the time. And for professors, that's really by doing research. On the other hand, the industry scene is kind of very much alive here. There are a lot of companies that are doing a really good job. So what I'm doing now, I'm kind of straddling this divide between, I like teaching, I want to be in academia from that side, but I also want to keep in touch with what's happening in industry. And I'm kind of between those two worlds. I don't know where the future might lead, but I kind of have to adapt to where I am and understand what the faculty job means here. And, is that what I want, and so on.
Certainly.
But something that basically I should have said first is, Back when I did an internship with Microsoft, I kind of had an offer to stay there. And when I was just graduating, I was thinking of interviewing also for some companies in New York. Most of my colleagues did that. But at that point, I was a little bit tired of the US, to be honest. I was there for 6 years and I felt like if I stay, that will be, I'm starting my life there and I'm just going to stay there. I didn't want that lifestyle. I'm very much attached to my family here and the way of life that we have here that is a little bit more, like a European, a little bit more relaxed. I think quality of life here is really good in some things that I consider to be important. So for me, I would say that private thinking is what really influenced my decision to not, go to Microsoft or Google or one of those companies and come back here. I would say that was the main thing.
Thanks for sharing those personal and professional stories. And I guess that you mentioned that besides teaching, you also have a couple of administrative duties. And when I saw that during your time at SSIT, you also helped the department to develop some of the collaborative research and teaching ideas with University of North Carolina and Charlotte, right? Can you just talk a little bit about some of these, collaboration projects that you have contributed?
What happens is that both SSST and IUS, where I employed now, they're both young universities and they're very tiny institutions, especially SSST. And if you work at such a university, it means that it's not well established. It doesn't have many of the divisions that a normal university would have. So you end up being a professor, but you're also doing many other things to kind of help it, thrive. And one of those things was I was helping establish a data science master's program in collaboration with the University of North Carolina. And the connection was actually a professor who was a Bosnian, but he worked in the University of North Carolina. So we established this joint curriculum and the program was running for a couple of years. But to keep something running, to have professors from there come over and give these hybrid lectures where you have local professors and foreign professors, you need a lot of finances. So it comes down to money a little bit. The program is still running in terms of curriculum, but I would say it's not that much integrated with North Carolina anymore, simply because the logistics of things didn't really work out.
Also at SSIT, you taught multiple semesters of data structure, introductory algorithms, advanced algorithms, and then algorithm and data structure for big data. At a very high level, what are some of the essential concepts and methods you cover in these courses?
Well, with data structures and algorithms, it's basically the basic problem-solving paradigms like divide and conquer, dynamic programming, recursion, graph algorithms, backtracking, a little bit of like NP-complete problems and stuff like that. And the algorithms for big data, that's this course that, or should I call it algorithms for massive data sets, is the course that led to me starting to write the book for Manning, because I was collecting the notes for that course and I thought to myself, there is no single book that covers all these topics in one place. So that's how this book is happening now. Basically, algorithms for big data is about succinct data structures. Basically, how do you reduce the size of data if you have a really huge data set? Or how do you sample data, how you work with streaming data sets, how do modern databases work, and so on. Those are some of the main topics.
Perfect. So since 2017, you have been an assistant professor of computer science and software engineering at the International University of Sarajevo. Can you just give an overview of some of the computer science department at IUS?
IUS has a really big we're the largest program at IUS. So we actually have both computer science and software engineering programs. Computer science is more about the fundamental topics and algorithms and hardware stuff like computer architecture, operating systems, and so on. Whereas software engineering program is more like applications, is more oriented towards software development, data science, and so on. So we have those two programs, and they're the biggest programs at the university. And one of the cool things at IUS is, we have really good students. And recently, we just started with a group of students. I started developing this website for improving programming skills for Bosnian youth. So that's one of the great things about being a professor. If you have a good idea and you have a couple of students who are interested in your idea, you can kind of make it happen. You are in touch with the smartest young people when you work at a university. Also, something that's really good about IUS is, of course, classes are in English. So we have a lot of international students and we have a lot of cross-departmental collaboration. Just because it's such a small university, then professors really have to work with each other. When you have a computer science program that has 50 professors, then you have your own building and you never get to see people from another building. But when you're all in one building, both electrical engineering and biomedical engineering and architecture and so on, then you kind of have lunch together. Some new ideas are born, and throughout just daily discussions, you come up with ideas on how to collaborate across different areas.
I see. At IUS, you have taught undergraduate classes on in-short programming, human-computer interaction, and algorithm and data structure as well. What are some of the types of problem and projects that students can learn from these courses?
I'm kind of teaching almost the same courses that I used to teach at SSSD, but a little bit also of the more practical courses like programming. And that's one of the biggest courses in the school because a lot of people who are not computer scientists are taking them. We have students from literature who are taking Introduction to Programming and students from architecture. So that's, for me, a really exciting class to teach. For human-computer interaction, that's one of the project-based courses where students actually get to think about users and think about user-centered design. This is a kind of a different sort of a course than algorithms, where you're teaching. Human-computer interaction is very project-based, and I've learned that the more I get out of the way and the more I let students, work on their stuff, they learn more. So the idea of being a professor has kind of changed over time, because before it used to be the, sage on the stage kind of thing. And, the better your lecture is, the better the class is. But now it's more about making students do the work. And something that I can say I'm proud of is that our students already in their third and fourth year already have jobs and they have multiple offers. And so I'm happy that even by their third year or second year, they're able to gain practical skills to the extent that they can get employed.
Now I want to move on discussing your news project. Currently, you're writing this technical book with Manning called Algorithms and Data Structure for Massive Dataset, which introduced data processing and analytics techniques specifically designed for large distributed datasets. What has been some of the biggest challenge that you encountered during the writing process thus far?
The biggest challenge? Well, I would go back to the thing that I said earlier about how I think examples are crucial when you're teaching. That same way, when you're teaching algorithms, the hardest thing for me, but also I think the most useful thing when the reader is reading your book, the most useful thing is a good example and a good use case scenario. So the way our book works is that it is introducing a number of techniques for engineers and data scientists and developers who are working with really large amounts of data. So how can they handle, what are the algorithms and what are data structures for handling such huge amounts of data? That topic can get abstract really fast because it has some of the sophisticated algorithms, but it's really important to show a use case from industry. So for example, if you're teaching Bloom filters, it's really important to say how Bitcoin uses Bloom filters or how Google uses Bloom filters. So you want to give a real example, but you also want to make it very specific with specific numbers, with specific, what plays a big part in doing a good example are illustrations. So this is a book I'm co-authoring with Emin Tahirovic, and also we have an illustrator, her name is Ines Dedovic, And she's doing these amazing illustrations. I mean, it's not up to me to say that our illustrations are amazing. I'm saying Ines's illustrations are amazing because she's both a technical person and an artistic person. So when I'm explaining a concept to her of what she should illustrate, she kind of understands because she's an engineer herself. Putting all of that stuff together is what's the challenging part. Getting an example that is interesting, that is realistic, and that teaches you something important on how to use a particular data structure is the key thing. If you can teach that well, then the rest of the text and, explaining how the algorithm works and stuff like that, I would say that's easier than this part where it comes to this algorithmic engineering, where you're putting together the real world of, Google and Twitter and Instagram and, IoT applications with an algorithm that's usually taught in a theoretical sense. I wanted to write a book where after reading it, somebody can say, okay, I know where I can use this thing. Not only do I understand how it works, but I know where I can use it. And so kind of teaching that part is, I would say, the most challenging.
Yeah, thanks for sharing the importance of illustration and emphasizing on the real work case study that you intend to bring about to the audience. Next couple of questions, really just kind of go over some of the table of content within the book. I have a chance to kind of briefly review the website. The first part expand on data sketches, including concepts such as hash table, approximate membership, Bloom filters, frequency and cardinality estimation, count mean sketch, and hyperlog. Can you just briefly, explain some of these concepts for the uninitiated?
Sure. So basically, the best way I believe to understand these data structures is to understand what's their purpose. Normally, if you have some set of data, let's say you're working with Twitter comments or tweets, let's just say. So if you had that kind of data set, you would normally want to analyze it for some features, for some keywords. You would want to eliminate duplicate tweets. You would maybe want to learn about things like who is tweeting the most, how many different users do we have, and basic questions like that. So with a data set that's not too big, you would normally achieve a lot of that with certain hash tables, with counters, with some common data structures taught in the algorithms class. However, when you have a lot of data, you have to be willing to lose some of that precision. So Bloom filter is something that's going to let you answer the membership query. Basically, is the tweet in the data set or is it not in the data set, in a much smaller space than a hash table. Now, something that these sketches have in common is that sometimes they make a mistake, right? Just because they're so tiny and they are allowing you to store so much information in such a tiny space, means that they will have some amount of error, but you can also control that error. So count min sketch is the thing that would let you answer the question of who's tweeting the most, or if you're analyzing on Amazon, what books are bestsellers? Give me a list of bestsellers. That would be count min sketch. Hyperlog is something that's related to the element distinctness problem. So if you have a bunch of tweets, but some people are tweeting multiple times, right? So you want to know how many different people are tweeting. So that's hyperlog. That's basically the summary of those sketches. So sketch means exactly that. It gives you the essence of the data, sometimes a little bit with a little bit of error, but it saves a lot of space. That's kind of the idea.
I see. The second part of the book looks at real-time analytics, more specifically techniques to handle streaming data. So what do you plan to cover here?
So that second part is actually being written currently by the other author, Emin Tahirovic. So I am not the expert on that subject, but broadly speaking, I can say that when you have streaming data, that means that this is usually in systems that are producing data all the time, like you have stock market or you have sensor data or so on. So the amount of data produced is enormous. So you can't keep all of it. So in some sense, this data is basically flying by you in some sense, and you are trying to capture the most relevant aspects of it. So you don't need to keep all of the data. You just need to extract what's most important about it and then throw it away. So this is kind of different from regular algorithms where you have all of your data and you can go through that data as many times as you want. With streaming data, you can just see it once, extract something, and then throw it away. What's being covered in that part of the book is what are the most effective ways to get the gist out of data. So producing histograms, sampling the data, quantiles, and stuff like that. So basic statistical features of streaming data. What are the best algorithms to derive those? That's the second part.
The third part of the book reveals some data structure for large databases and external memory algorithms. I noticed that these are some of the stuff that you work on during your PhD, right? Would you mind just giving an idea of some of the topics that you want to write about?
Yeah, basically, you're exactly right, James. So the third part is in external memory algorithms, and basically talks about how modern databases work. What are the data structures that power those databases? And today, if you're a developer, you're not likely to be developing your own database engine, right? You would be using something that's out there already. However, if you learn about data structures that exist underneath those engines, then you would be more likely to be able to differentiate between what is the right database engine for your application. So, for example, some database engines are optimized to process a lot of inserts. So think about, I don't know, Dropbox or any kind of backup software. There you are just storing a lot of things all the time and adding new stuff. Sometimes they need to roll back and look at what somebody added a long time ago, but most of the time you're just adding new stuff. So that's a very different workload than a workload on Google where stuff is being added all the time, but also stuff is being queried all the time. So you need to be really fast at answering a Google search query as well as adding new stuff that's being indexed by Google. So the goal of that third part is to show what data structures are at work depending on what kind of workload might be in case. So that's kind of the big picture.
I see. Yeah, I'm very excited to see the book coming out this year, and hopefully we can go over them in the future. We'll also be sure to put a link to the book into the show notes. Listeners who are interested in kind of look over some of the part that already finished, check it out and learn about some of these techniques that Jayla just mentioned in her answers. Maybe we'll talk about like this throughout the chat, but can you just share a bit about your thoughts regarding the tech community in Sarajevo?
Actually, there's been a kind of a tech boom in Sarajevo recently, and it's a really exciting place to be from that perspective. On one hand, Bosnia has very bad unemployment figures, very high. However, tech is the only sector where unemployment is close to zero. As I've mentioned, our students, even before graduating, they have a job. So for Bosnia, it's one of the strategic sectors of, you don't need much investment for the country to advance as you would need if you were investing in something else. So there's a lot of young people now studying technical sciences and even people switching from different fields to tech. So I would say it's definitely the most promising sector in this country. Something that maybe is not that ideal as much as it is in the US is that most of the work done by the software companies is outsourcing, right? So the US companies outsourcing pieces of software development. Usually the part that you outsource is probably not the most exciting part. I don't see a lot of super exciting algorithmic challenges in the companies, but that's changing. That's also changing very quickly. So I would definitely say it's developing. There's a lot of work to be done, and there's a lot of need for skilled labor force. That's one of the main issues because, you can't grow a tech sector without having a lot of people who know how to do coding. So that's where the importance of kind of education and online education comes in.
Thanks for sharing your thoughts on that. And I think your role as an educator is really important because, promoting the technical education is the fundamental step in order to ensure that there's talent and making sure that the tech industry within your community can bloom, right? So, Jella, at this point of our conversation, I want to move on to the final closing segment, in which I'm going to ask you three rapid fire questions, and then you can give quick answers for the listeners. Number one, name three people in the algorithms universe whose work you admire.
Three people in the algorithms universe. Well, that goes back to my grad school. I remember one of the people who were really awesome were Eric Demain, was a professor at MIT of algorithms, and I remember learning a huge deal from his online lectures. This was MIT OpenCourseWare back when not so many schools opened up their classes to the world. He was somebody and is somebody. I don't follow his work so much anymore, but I remember at the time he was somebody who collaborated with all kinds of scientists and artists. So I remember he wrote a book about algorithms for origami, like how do so he was one of those kind of interdisciplinary, amazing Renaissance people. And I learned so much from his lectures. So that's one person. I would say I also admire my advisor and his whole team of researchers that I got a exposure to work with. I'm really lucky. I feel really lucky for that, for kind of being able to take something that's algorithmic and theoretical and turn it into a product. That's something that I learned a lot from. There was a professor at Stony Brook called Joe Mitchell, and he teaches computational geometry. He's an amazing professor and an amazing educator. I don't know why, whether he didn't have his video lectures up at the time when I was a student. I don't know if he does yet, but he should if he doesn't. I loved his lectures. I know many students who went to take his course multiple times, just the same course, just to be there and listen to him, because he also had a lot of cool stories. Also, Professor Steve Skeena. I'm naming some of the people, like I was his TA, and I also learned a lot from that experience at Stony Brook. Now, some of the other people outside of Stony Brook were Jeff Erickson is a professor at Urbana-Champaign, University of Illinois, Urbana-Champaign. And he's kind of a renegade, like a rebel in that whole area. So he has really cool notes and lectures. I learned a lot from that. I guess, yeah, that's maybe my top 5 list, not top 3.
Be sure to include all those profiles in the show notes. Second question, name one book you would recommend for people to develop a better algorithmic mindset.
Well, you mean except from my book. No, just kidding. A book I use for my algorithms classes is I use a lot of books as reference, but the main textbook that I use is the Algorithm Design Manual by Steve Skeena. It's really written in a way that it shows you mathematical intuition instead of the theorem proof type thing. I would say it's really practical and fun and easy to read, so that's something I would recommend.
Then lastly, imagine that you can send out a tweet to all the aspiring academic professors on Twitter. What could you tweet about?
Wow, I don't know. Maybe I would say something along the lines of, like, don't neglect your programming skills or something like that. I think at this time, you would really have to be a super amazing theoretical scientist if you want to get away without coding. Right now, those skills are really important, even if you're in academia. So I would say always, if you're in grad school, if you're studying to be, a professor, just make sure you also keep abreast with what's happening in the real world. What are the tools? What are the languages? And what are the skills that are important there? Because as time goes by, I think the traditional notion of a professor that we're used to is going to be gone. And it's kind of, happening even today. People are learning more using online platforms from people who don't have PhD degrees a lot of the times, and they're learning really useful, cool stuff. I have learned a lot from courses in Python or something or other languages from people who don't even have a PhD degree. So the landscape of education is changing really fast. So I would say a lot of people are attracted by this job safety in academia. Like if you get a job and if you get a tenure, your job is there forever. But I think that that kind of thing is going away. The world is moving really fast. So I would tweet, this would be a really long tweet, but basically don't neglect the real world skills would be my tweet.
Yeah, that's a great way to end our conversation. And I think that's probably like applicable to anyone in the academic world as well. So Jill, I really appreciate you spending time with me today, discussing a bit about your journey into studying computer science from your background, discrete math, your PhD at Stony Brook, some of your interesting research on both the theoretical side and experiment and building algorithms and data structure for large-scale dataset, your passion for teaching, some of your professorship at SSIT and IUS, and along the lines of the book that you're currently writing with Manning. I'll be sure to include all the links and resources that we discussed throughout this podcast into the show notes, so listeners can have a chance to take a look and check out some of Jela's works if they're interested in. I really enjoyed this conversation, and I hope you have a great rest of the day.
Cool. Thank you so much for having me.
Well, that's the wrap for another episode of Datacast. Hopefully, you have learned something insightful and interesting from my guest today. You can read the show notes from the podcast website at datacast.simplecast.fm. If you want to get instant updates when a new episode is released, either follow me on Twitter or subscribe to my newsletter on my website jameskelly.com. It is my greatest pleasure that you listen to this podcast and take advantage of the data revolution coming upon us. Goodbye for now.